Okay, good morning, everyone. I trust there were no issues with the homework last night. A couple of, not, about 4 to 5 students reached out to me with minor questions, but overall, I think pretty much everyone got the answers correct. Okay, so first thing I want to do today is just take 1 or 2 minutes to show you the updated final exam page. So let's see. Okay, yes, the final is worth 20%. I think I'm in the wrong. Okay. All right, so final exam page has been up since the beginning of the quarter. It is accessed right from the front page. If you click on the final exam page, it'll take you to this page as outlined in bold, big letters on the front. Please read everything on this page. Okay, it is mandatory, it's not optional. As outlined on the first day of class and in the syllabus, it's worth 20% of your grade, of your overall grade. It is mandatory in the sense that it will not be dropped. Personal decision of taking the final or not is up to you. If you do not take it, you just on a 0. If you're happy with your grade as is, that's up to you. Okay. There is no Zoom option. All final exams are in person. So unlike quizzes and the homework assignments, there is no online option for a final exam. You have to take it in person. And there are multiple options for students. Again, I went over this on the first day of class, so I won't go too deep into it. You can take it at your regularly scheduled day and time, which is the schedule set by Cal Poly. Faculty have no control over the scheduled final days and times, okay? So you are section 02, meaning your university scheduled time for the exam is Wednesday, March 20th at 7 o'clock in the morning in this classroom. Okay, it's 7 to 10 on a Wednesday. You can also look at these two links. There's a downloadable PDF, and this is the website where Cal Poly posts the entire schedule for finals. So again, you can use this for your other classes also. But again, section 02, 9 o'clock in the morning, meets at 7 o'clock on March 20th to take their final. You have the option of taking the final with the other two sections, which is again, Wednesday, same day, just starts at 10 o'clock. Okay, so if you don't want to get up early in the morning, you can come and take the exam at 10. Yes. Yes. Yeah. So I'll get to that. First, I just wanted to cover the other sections, right? So we have plenty of space in here. I don't foresee a problem. So if you wish to take it at 10 o'clock on the Wednesday and not at 7, that is absolutely fine. I will, however, need students to fill out forms if you are taking it at an alternate time, just so that I don't run into a problem. As I said, I do not anticipate running out of physical seats, but it's always good to be prepared beforehand. So again, you can take it on a Wednesday at 7, you can take it on a Wednesday at 10, or you can take it on a Friday of that week at 10 a.m. It's not p.m., it's 10 a.m. The other option is if you wish to take it on a Saturday, then that's the Saturday before finals week. Okay, that's a Saturday before finals week. Again, these are all options that are presented to students. So if you want to take it on a Saturday before finals week, that will be in a different location. It will not be here. Okay, it will be in the EE building, building 20, where my office is. And several students signed up and let me know that they wish to take it on a Saturday. All the final exams, all 4 of them will be similar, but different. Okay, the level, it's not going to be harder or easier if you take it earlier or later. They'll be very similar in structure. The problems would be similar. Concepts that will be tested or assessed will be similar, but of course there will be differences in each of these exams. Is there a question there? So it's down the page, but there was a question back. Yeah, you can do that. So all the topics have been listed here. As I promised, I will not test on chapter 6. Okay. Chapter 6 will be assessed in the next week. So it will not be assessed on the final separately. I mean, it won't be tested on the final equation sheet, and that's the survey at the bottom. Okay. As I said, several students had signed up on the first week of class itself. You do not need to fill out this form. You do not need to submit this if you are taking the final at your regular scheduled time. Meaning if you're taking it on a Wednesday at 7 o'clock, you do not need to submit this form. Only submit this form if you wish to take it at an alternate time. Especially if you wish to take it on a Saturday, I need to know how many exams to print and how many seats I need to make available, because it's going to be in a different room. Okay. So if you wish to take it at an alternate time, please fill out or submit this form at least by Wednesday of next week. Okay. At least by next week. All right. So that's for the final exam. Again, read through everything on this page outside of class. And then let's proceed with our chapter 6 topics. All right, so we stopped right here, which was the frequency response, determining the frequency response of a network based solely on the transfer function information given to us. Okay, so from now on, let's look at how we can use inductors and capacitors as filters. I have this small table right here, which describes the behavior of an inductor and a capacitor at extremely low frequencies and extremely high frequencies. Okay, and this is the table that you can use to do a very quick analysis on any circuit. Okay, so if you apply an AC signal or a bunch of AC signals to a circuit containing inductors and capacitors, you can use this table and you can do a quick analysis within like 2 minutes. Okay, so at extremely low frequencies, when the frequency or omega tends towards 0, capacitor behaves like an open circuit. Remember, for DC applied voltages and currents, capacitor is an open circuit, or as I like to say, OC. Yes. Yes, it's on there. It's on the final page. Yeah. Equation sheet, both sides of a standard paper. Standard letter paper. Yeah. So where was I? Oh, yeah. Open circuit, or OC for short. And at extremely high frequencies, capacitor behaves. At extremely high frequencies, capacitors behave like a short circuit, or SC for short. So as the frequency tends towards 0, it behaves like an open circuit. As it tends towards infinity or very high frequencies, it behaves like a short circuit, which is basically, if you remember, ZC is 1 over J 2 pi FC, right? ZC is inversely proportional to the frequency. ZL, impedance of an inductor, is, however, the opposite. J 2 pi FL, meaning it is directly proportional to the frequency. So as frequency F tends towards 0, inductor behaves like a short circuit and behaves like an open circuit for extremely high frequencies. So again, you do not have to memorize this as long as you understand how to use the table. Okay. And, as with anything in life, if you practice long enough, if you look at the same thing over and over again, at some point in time, it just gets ingrained in your brain, right? So you can think of this as quantitatively using the equations, or you can think of it from the point of view of semiconductor physics. If you remember, going back to chapter 3, right? Capacitor starts charging. Once it reaches full charge, there's no more charge imbalance for a constant steady state applied voltage, and then it behaves like an open circuit. So based on this table, you can actually design multiple filters. Okay, and these are the filters we will study in this class. Low pass, high pass, band pass, and band stop or band reject filters. Okay, The filters that we will study are made of capacitors and inductors. There will always be resistors in the circuit. So similar to chapter 4, you would have RC and RL filters. And you can configure both types to work as low pass as well as high pass. So it's a cross matrix of like 4 filters. If you use a capacitor and a resistor to build your circuit, it is a RC filter, and you can have low pass RC filters as well as high pass RC filters. If you use an inductor and a resistor to build your circuit, then it's a RL filter circuit. And you can build, again, a low pass as well as a high pass RL filter circuit. Okay. If you combine both of those components together, or in fact, not just components, if you combine both these filters together, low pass plus high pass, you get what is known as a band pass or a band reject filter or a band stop filter. Most filters that we use in everyday life would be a band pass filter. Okay, there are certain band of frequencies that are allowed to pass through. Yes. Frequency, yes. Good point. Yeah. So the low and high refers to the frequency F or angular frequency omega. Also, think back to chapter 4, where I said, if you have one energy storage device in a circuit, it requires a first order differential equation for its solution, and hence it is known as a first order circuit. So similarly, if you have one energy storage device or one filtering component in your circuit, it is known as a first order filter. So RC or RL filters are first order filters. Okay, first order filters. If you have 2 of these components, whether it's 2 capacitors or 2 inductors or a inductor and a capacitor, it's 2 energy storage devices, requires a second order differential equation. So it's a second order filter. Second order circuit is a second order filter. And in the next few slides, we'll understand how the order of the filter affects the performance. There are n order filters going up 3rd, 4th, 5th, 6th, 7th, and there are trade-offs. Okay, the higher the order of the filter, the better it approximates an ideal filter or an ideal circuit. Okay, filters, again, as with any mechanical filters, are supposed to block certain things and allow to pass certain things, right? And so the slope of the block and the pass band would be a straight 90-degree angle. Whether it's low pass or high pass or band pass, doesn't matter. But in real life, you would never have a sharp transition, right? It will always be a gentle slope. And so a higher order filter will approximate the ideal characteristic of a ideal filter. Again, this is not an EE class. We will not study higher order filters. The only filter of higher order we look at is the RLC circuit, which is a second order filter. All right, 10-second pause. Let me know if you have any questions so far. Does everybody understand the concept of this table? Component behavior. Okay. So I will use that when we get into our circuits. So here is a first order RC filter. It's a first order RC filter. The reason it's RC, of course, is because we use a capacitor and a resistor in the circuit. Okay, resistor and a capacitor in the circuit. So let's use our, what I like to call the handy dandy table. A handy dandy table. First, let's look at extremely low frequencies. So at F equal to 0 hertz. Capacitor behaves like a, anyone? Open circuit. Capacitor behaves like an open circuit, right? F is equal to 0 is DC, meaning no frequency, no time variation. And so it behaves like an open circuit. You can have this table on your equation sheets, by the way. Okay, you can have it on your equation sheets. So if the capacitor behaves like an open circuit and I redraw my circuit, what do I get? I have a voltage source connected to a resistor R. Capacitor is open. My V out is simply equal to V in. Note that all of these are phasors. Okay, we will still be using complex math to solve. Again, this handy dandy table is used to quickly analyze a circuit, okay, to perform a very quick analysis. So there is no other mathematical or quantitative equations or solution that go along with this. So V out is equal to V in for low frequencies at F tending towards infinity. Capacitor behaves like a short circuit. This capacitor behaves like a short circuit. What is my V out? 2 points are connected together and I try to measure the voltage between those 2 points. What is the difference in potential? It's 0. So V out is equal to 0. Hence, I can say that the circuit works as a low pass filter. It is allowing the low frequencies to pass through. I obtain V out at low frequencies, and at high frequencies, V out goes to 0. Yes. Short circuit. Yes, short circuit. Capacitor behaves like an open circuit. Capacitor behaves like a short circuit. OC and SC. Let's take a 10-second pause. Again, you can analyze any kind of circuit which has capacitors and inductors using that table, okay? Especially if you're trying to use it as a filter. All you do is you simply look at the table, describe the component behavior at low frequencies and at high frequencies, and you replace the capacitor with an open circuit or a short circuit. And then you just redraw the circuit diagram and, well, analyze. Okay, any questions? Any questions at all? So we established that this works as a low pass filter, right? Again, this is not a quantitative explanation. This is just a qualitative explanation, right? Quick and easy qualitative explanation. Now let's look at what is happening in the circuit. If you apply voltage V in, we'd expect current I to flow in the circuit, right? And because this is a series connection, the current I is the same for the resistor as well as the capacitor. It's the same current I, right? There's no difference. Remember, just because we are taking the output here does not mean there is anything connected to it. We are simply measuring the output across the capacitor, but there is no component connected at this node. If there is no component connected at that node, the resistor and capacitor are in series. If they're in series, the current through those components is exactly the same. Okay, the current through those components is the same. So the current is the same. We can apply Ohm's law. And again, there is a derivation that goes along with this, which again, we don't do these derivations for non-E classes. But we simply apply Ohm's law, and I can find I, or the phasor for I, as V in divided by R plus ZC. which is the impedance of that capacitor, 1 over J 2 pi FC. Okay, 1 over J 2 pi F times C. So it'll be V in divided by R plus 1 over J 2 pi F times C. And then to find the voltage across the capacitor, all we do is, so V out is equal to VC, and VC is equal to I times ZC. We would simply plug in the value of I, or this equation for I, and you plug in the equation for ZC, we would reduce it, and we would obtain an expression for the transfer function that looks like this. Okay, we'd have V out, we have V out, and we'll have V in from here. V out over V in gives us the transfer function h of f. So we rearrange the terms, all of the terms, to give us a ratio of output to the input voltage, which is nothing but a transfer function h of f. Okay, h of f. And we'll end up with an equation that looks like this. H of f for a low pass filter is 1 over 1 plus j f over fb, where fb is given by 1 over 2 pi rc. FB stands for break frequency. Break frequency. It is also known as the cutoff frequency, FC. FC, that C is a subscript, stands for cutoff frequency. Okay, cutoff frequency. So if you hear the words or read the words cutoff frequency, it means the break frequency FB. That is the point where all frequencies are either passed or blocked. So if it is a low pass filter, an ideal low pass filter will allow all frequencies lower than FB to pass through to the output. Okay, so if FB is here, this is frequency in hertz. If FB is, well, depending on the design of the filter, if FB is somewhere here, all frequencies lower than FB will be allowed to pass through. So this is pass, and all frequencies higher will be blocked. So all frequencies lower than FB will have a output of, this is V out, this is V out. So V out would be equal to V in for all frequencies lower than FB. And all frequencies higher than FB would be equal to 0. This is, of course, the ideal characteristic. Okay, hence the term low pass filter. The break frequency defines where the filter will cut off the frequencies or the input signals. For a low pass filter, all frequencies lower than the cutoff frequency or the break frequency will be allowed to pass through. For a high pass filter, it's the exact opposite. If you have a break frequency, it will allow all the filters, all the frequencies higher than the break frequency to pass through. All the low frequencies will be blocked. All right, 10-second pause. Let me know if you have any questions. Does this make sense, explanation? Okay. This is, of course, for an ideal filter. A real life filter, of course, is not ideal. And so those characteristics appear like this. If you plot the magnitude of the transfer function for a first order filter, first order low pass filter, as a function of frequency, it looks something like this. So an ideal filter would be like this, whereas a real life filter will have a slope. Okay, this is ideal. And this is the real life. Now, there are many ways to plot the output of a filter. You can plot V out, voltage as a function of frequency, right? You can plot magnitude of the transfer function, H of F, versus the frequency. There's also something we will see later in this chapter known as Bode plots, okay, where again, you're plotting the magnitude of the transfer function versus the frequency. Okay, so in all cases, the graph or the response will look very similar. Low frequencies will have a high voltage or high value. Higher frequencies will slope towards zero. The phase is also affected. If you look at the phase, it goes from 0 degrees tending towards minus 90. Okay, from 0 degrees tending towards minus 90. Since real life filters do not have a sharp cutoff, we describe the distinction between a pass and a block band, meaning pass band, frequencies which are allowed to pass, and the frequencies which are blocked, we describe in terms of where the power drops to 50%. Okay. Again, remember, ideal filters, there's a sharp cutoff, goes from max to zero, right at the break frequency. But real life filters do not have that. They have a gentle slope. And so because of that slope, we have to place a block where we have to describe where we consider as the pass band and the block band. And so that point is selected as where the power, the output power drops to 50% of the input power. And in terms of voltage and the transfer function, that comes to 0.707 or 70% of the input voltage. Then V out drops or is equal to 70.71% of V in is our cutoff frequency FP. That separates the pass band from the block band. If you notice in this graph, after FB, ideal filter after FB would be equal to 0, but real life characteristic, we still have some output, but we consider that to be blocked. Okay, it is still passing on some value of the input to the output, but we consider that to be as block band. We consider that signal to be blocked. Okay, so again, that's the difference between ideal and real. Yes.
What is the trade-off for using a more expensive filter, using a shorter circuit, like more power consumption, or?
There's all sorts of considerations. Power is one of them, yes. More components, more expensive components would require, well, again, it's in there, more expensive components. Higher order filters also, the characteristics are sometimes, so if it's like this, and you go higher order filters, starts to give a sharp current, but then there is a weird bump that appears right before. So it's just a trade-off on, and of course, it depends on the application. As an example, Remember, I was talking about, when I introduced this topic, I talked about the crossover network in speakers. Expensive speakers, especially like three-way crossover speakers, will have big inductors, high quality inductors with low resistance, resistors, high quality resistors, big high quality capacitors. If you look at the cheap ones, which are like really small speakers, which are two-way speakers, especially the ones in a home theater in a box system, they will sometimes just have a capacitor and a resistor simply glued on top of the speaker itself. That would not be like a separate circuit box or, nothing like that. Just a cheap capacitor and a cheap resistor mounted directly on top of the there. So it's just doing a basic filtering, but it's not, providing like a sharp cutoff or anything like that. So a transition between the pass and the block band would not be as sharp. And so the sound that you hear from those speakers would not be as good. Let's see. RL low pass. Let's go to RC high pass. Okay. So we looked at the RC low pass filter, right? Now look at the RC high pass filter. What difference do you notice between the two circuits? This is RC high pass. This is RC low pass. There's actually, the configuration, yes. It seems as if it's different. Actually, there is no difference in the circuit. There is absolutely no difference in the circuit. It's exactly the same circuit. This is the low pass, and this is the high pass. You have a capacitor connected to a resistor in series. You're applying a voltage signal to that series connection. The only difference is where you are taking the output. So you have a resistor and a capacitor in series. You're applying a voltage, and the only difference is where you take the output. It took me, I think, when I was a student, I didn't realize this until the next year after I had already taken this class. And so some things are not as obvious. It's the same RC circuit. You apply a voltage V into it. If you take the output across the resistor, you get a high pass filter. If you take the output across the capacitor, it is a low pass filter. And that's it. There's absolutely no difference. It's a series connection of components. You apply voltage V in, and you take the output across the resistor. It's a high pass filter. If you take the output across a capacitor, it is a low pass filter. And we'll do the quick and easy analysis with our component. So at low frequencies, and now I'm talking about this circuit, this output right here. At F equals 0, capacitor behaves like an open circuit, right? So if capacitor behaves like an open circuit, nothing is allowed to reach the output. So V out is equal to 0 volts, right? V out is equal to 0 volts. And conversely, at F equals infinity, capacitor behaves like a short circuit. And if it behaves like a short circuit, well, then V out would be equal to V in. Meaning, at low frequencies are blocked, high frequencies are allowed to pass through, hence high pass filter. Let's take a pause, think over it. Let me know if you have any questions. Again, it might take some time for that handy dandy table to sink in, but once it sinks in, you'll be able to like analyze any circuit with inductor and capacitor. Capacitors behave like an open circuit at low frequencies and as a short circuit at high frequencies. And so you simply substitute that component with its behavior at both f is equal to 0 and f is equal to infinity, and you can see what the output would be. All right, any questions? Does it make sense? Again, there is no quantitative equation or discussion right now. There is just qualitative description, right? It's the exact same circuit. We have a series connection of a resistor and a capacitor. You apply voltage V in, or a signal coming in with different frequencies. If you take the output across the resistor, you get a high pass filter. If you take the output across the capacitor, you get a low pass filter. And that is what happens in a, going back to the point about, inexpensive speakers. You have a two-way speaker, like a cube speaker, small one. If you want to apply a filter to it, all you do is you take a resistor and a capacitor. I swear to you, I've seen speakers where the capacitor and a resistor, like the leads are just twisted. There's like no other connection. It's just twisted. And then you take the two outer leads and they're plugged directly onto the speaker. And it's as easy and as cheap as that. Like real life crossover networks, again, are like heavy inductors inside the speaker box. But it's very easy to implement a filter using a capacitor and a resistor itself. Because again, the same component or the same circuit provides you both high pass as well as low pass. So if you have a small two-way speaker like this one, I'm assuming this is expensive, or at least not as cheap as the ones we use at home. So you just have a capacitor and a resistor, and you have both a high pass as well as a low pass filter. Does that make sense? Any questions? Any questions at all? Okay. Well, the equation for the transfer function, again, we won't do the derivation, but it's pretty similar. The current I, you find the voltage, you find current I by applying Ohm's law first. Total impedance in the circuit is ZC plus R. Again, it's the exact same circuit, but this time you're taking the output across the resistor instead of the capacitor. And so VR would simply be I times R. And in the end, you end up with a transfer function that looks like this. FB, the break frequency, still remains the same. It is 1 over 2 pi RC. Yes. This is the high pass filter. Yeah, the transfer functions are different. So for an RC filter, the break frequency equation remains the same. It is 1 over 2 pi R times C. Okay, R times C. But the transfer function is different. It's JF over FB. So there is an extra component in the numerator. It is JF over FB. Okay, JF over FB. The denominator stays the same, 1 plus JF over FB. It's a complex quantity, hence the imaginary term J. Okay. If you solve this equation at F is equal to FB, FB is a constant, right? It's 1 over 2 pi RC. Engineering designers will actually design it based on the requirements, but the component values are fixed. So FB is fixed. F is the variable. So the transfer function is a function of the incoming frequency F. So when F is equal to FB, you get J in the numerator divided by 1 plus J. And when you solve it, again, you get 0.707. Okay, so the transfer function drops to 70.71% of the incoming voltage when F is equal to the cutoff frequency or the break frequency. All right. It's the same for the low pass as well as the high pass. The characteristic for a high pass filter is shown here. A real life high pass filter would have characteristic like this. Sorry, ideal high pass filter would have characteristic like this. This would be the pass band, and anything lower than that would be blocked. Okay. And then the angle for the transfer function goes from 90 and tends towards 0. For a low pass, it tended from 0 to minus 90. This one goes from plus 90, tending towards 0. At the cutoff frequency, both of those have a phase of 45 degrees. Low pass, it is minus 45. For a high pass, it is plus 45. Doesn't matter what kind of filter it is. At the cutoff frequency, it'll always have a magnitude of 0.707 times V in. All right, questions? All right, then let's look at RL filters. RL, just the combination of a resistor and an inductor. And similar to RC, it is the exact same thing. It's a series connection. It's a series connection of an inductor and a resistor. And you apply an input voltage to that series connection. If you take the output across the resistor, you get a low pass filter. If you take the output across the inductor, it is a high pass filter. And I have a diagram for a RL high pass filter right here. So if you take the output across the inductor, it is a high pass filter. If you take the output across the resistor, it is low pass filter. And we can perform the quick and easy analysis using the component behavior at low and at high frequencies. Okay. So at F tending towards 0, inductor behaves like a short circuit. If inductor behaves like a short circuit, I would obtain output. V out would be equal to V in. As F tends towards infinity, inductor behaves like an open circuit, and hence nothing is allowed to reach the output. V out equals 0. Hence a high pass filter. Low pass filter. Okay, it's the exact opposite of the capacitor. In a capacitor, RC filter, if you take the output across the capacitor, it is a low pass filter. In a RL filter, if you take the output across the inductor, then it's the exact opposite. It becomes a high pass filter. Right? Again, because they are similar components, but exactly opposite in many ways. Okay, the phase angle, the phase for a capacitor impedance and inductor impedance is 180 degrees out of phase. Always remember that. All right, questions? Any questions at all? No questions? The transfer function remains the same, whether it is RC or RL. The transfer function describes the behavior of a low pass filter. Okay. describes the behavior of a low pass filter. So RC low pass and RC high pass, they have exactly the same transfer function, 1 over 1 plus J F or FB, and the same for a RL filter, 1 over 1 plus J F or FB, no difference. The break frequency, however, is different. For a RL filter, it is R over 2 pi L. R over 2 pi L. Okay. So it's a low pass filter. It doesn't matter whether it's RC or RL. The transfer function remains the same. The break frequencies are different. When you get to the high pass filter or high pass RL filter, it has the same transfer function as the RC high pass filter. But the break frequency is the same as the RL filter. Okay, R over 2 pi L. Oh, one, I just like to point out again, omega is 2 pi F. So the same equations also work for omega. Okay, if you take a different class with a different book, instead of FB or FC, it would be omega C cutoff frequency in radians per second, then it would simply become R over L. Okay, you just divide by 2 pi because omega is 2 pi F. F is equal to omega by 2 pi. So if FC is R over 2 pi L or FB is R over 2 pi L, then the same equation in terms of omega is simply R over L. Inside the building or outside or what? Anyway, the cutoff frequency for a low pass in omega for RC low pass would simply be 1 over RC. Okay, so keep that in mind. Keep that in mind. Okay, any questions? Any questions at all? You looked at 4 filters. Any questions at all? Okay, I'll end class here today. We're almost out of time. I wanted to do one example problem. What I'll do is either, so it's right next. Okay, let me just do the summary though. So low pass, this is just gives you a direct equation to calculate the values for the magnitude as well as the phase angle. Okay, that's all it is. So that's 2 slides after the filter slides. And here is the example problem. So I will solve this example problem and I'll post a video and also post it on the slide itself. Okay. All right. So we'll end class here and I will see you all on Friday.
Yeah,